Have you ever pumped air into a bicycle tire and felt the barrel grow warm under your hand? That simple experience is a window into the fascinating world of thermodynamics. Hello and welcome. In this video, we are diving into applications of thermodynamics, the science that explains how energy moves and transforms all around us. From the heat in a pressure cooker to the expansion of gases in an engine, thermodynamics is working quietly behind the scenes. Today, we'll uncover how work and heat interact, why enthalpy matters, and how we measure energy changes. So, let's get started step by step. Let's begin with work, a core idea you'll encounter again and again. In thermodynamics, work isn't just any effort, it's often pressure-volume work, like compressing gas in a syringe or expanding steam in a cylinder. Picture this, you have a gas sealed in a cylinder. When you push down the piston, you compress the gas and its volume shrinks. Here's how we calculate the work done on the system. Work equals minus external pressure multiplied by change in volume. Let's walk through a quick example together. Suppose you compress gas from 5 liters to 2 liters under a constant external pressure of 2 atmospheres. First, find the change in volume. Delta V equals final volume minus initial volume, so to minus 5 equals minus 3 liters. Then, compute the work. W equals minus 2 times minus 3, giving plus 6 liter atmospheres. This positive sign tells us energy has been transferred into the system. So, next time you pump air or compress gas, you'll know exactly how to explain the energy involved. The quick insight is positive work means energy enters the system. Most chemical reactions don't happen in sealed containers, they happen at constant pressure, like in open beakers or flasks. That's where enthalpy, represented by the letter H, comes into play. Enthalpy equals internal energy plus pressure multiplied by volume. Written as H equals U plus PV. Why is enthalpy so useful? Because at constant pressure, the change in enthalpy, or delta H, tells us the heat exchanged with the surroundings. Delta H equals delta U plus P times delta V. Let's connect this to something real. Imagine burning methane in air. As the gas combusts, heat is released and the mixture expands against atmospheric pressure. The enthalpy change neatly captures both the internal energy shift and the work done to push back the air. It's a single, powerful measure chemists rely on to track energy flow. The quick insight is delta H is directly measurable in open atmosphere reactions. Before we move on, let's clear up a common point of confusion: extensive versus intensive properties. This distinction is surprisingly important. Times extensive properties depend on how much matter you have. For example, volume, mass, internal energy, enthalpy. Double the substance, double these values. Times intensive properties stay the same no matter how much you have. Think temperature, pressure, density. Here's a quick test. If you pour half a bucket of hot water into another bucket, has the temperature changed? No, it's still the same. But the volume? Held. Remember, extensive properties scale with size, intensive properties do not. The quick insight is test, divide system. If value house, it is extensive. Now, let's explore heat capacity, which tells us how much heat a substance needs to warm up. Heat capacity C is defined simply. Heat equals C times change in temperature. Or in symbols, Q equals C multiplied by delta T. Heat capacity varies depending on conditions. Times CV is the heat capacity at constant volume. Times Cp is the heat capacity at constant pressure. For an ideal gas, there's a neat relationship. Cp minus Cv equals R, where R is the universal gas constant 8.314 joules per mole per Kelvin. Let's see this in action. If Cv for helium is 12.5 joules per mole per Kelvin, then Cp equals Cv plus R, so Cp equals 12.5 plus 8.314, giving 20.814 joules per mole per Kelvin. This explains why heating a gas at constant pressure takes more energy. It has to expand too. The quick insight is heating at constant pressure requires more energy than at constant volume. Let's quickly wrap up what we've learned. Times work is the energy of compression and expansion. Times enthalpy tracks heat flow at constant pressure. Times extensive and intensive properties help us categorize thermodynamic quantities. Times heat capacity tells us how much heat is needed to raise temperature. Remember, from the warmth in your bicycle pump to the engines that power vehicles, thermodynamics is everywhere. In the next video, we will explore how we measure U and H experimentally through calorimetry. Stay tuned and keep learning chemistry the smart way. The quick insight is always convert L.atm to joules in numerical answers. Let's wrap things up by connecting the dots. We saw how work tells us about compression and expansion of gases. We saw how enthalpy captures heat flow at constant pressure. We compared extensive and intensive properties, and finally, we explored heat capacity, the energy needed to heat a substance. Now let me ask you, can you think of one place at home where all these ideas come together? Hint, it's in your kitchen. Yes, the pressure cooker. The steam inside does pressure-volume work. The food absorbs heat at nearly constant pressure, and you can even think about the heat capacity of the water and grains inside. Or imagine pumping up your bicycle tire. Every push you make is doing work on the gas. Did you notice the pump gets warmer? That's thermodynamics right in your hand. So here's the takeaway. Thermodynamics isn't abstract. It's the bridge between the chemical equations you write on paper and the energy you feel and use in daily life. Think about it. Where will you spot thermodynamics next? In the kitchen? On the road? Maybe even in a rocket launch video you've seen? Keep your eyes open, because energy transformations are happening all around you.